Thank you so much, Jethro, for the invitation, and thank you everyone that organized the seminar. So I'm more than happy to stay here today and to talk about the intersection of real Bruja cells. This is a joint work with Professor Nicolau Saldanha from PUC-Rio. And so I forget this. Let me see. Okay. So first of all, let me say that if I take two matrices in the orthogonal group, we say that they are Bruja equivalent if and only if there exist two upper triangular matrices, U0 and U1, that Q1 is equal to U0, Q0, and U1. So let me see if these things like have something, a pointer here, something, okay, good, so like this. So the equivalence class are called Bruja or Schubert cells. And a good representative in these classes are permutation matrix like this. So if you take a sigma, permutation, the Coxeter group, that we denote by Sn+1, we denote by P sigma, the matrix permutation defined like that. So if the image of I by the permutation sigma is J, you put 1 in the entrance Ij on the matrix and 0 otherwise. So in this case, for sigma, for permutation sigma, we define Bru sigma, the set of all orthogonal matrices that are written like that, where here we saw P sigma. So the intersection of Bruja cells appears in many areas, like singularity theory, Kazakh-Zanlux theory, and in the locally convex curves. So I studied the homotop type of locally convex curves in my PhD thesis. And so my interest in these topics more or less appear in here, in this point. And so in fact, what we are studying is the intersection of a top dimension, Bruja cell, with a cell of any dimension. And what happens is that these intersections are a subset of the lower triangular group. So I will explain in 5 or 10 minutes this sentence why these intersections are like that and why they are a subset of the lower group. So in fact, in this case, what you are studying is this set that we call BL sigma. So it's a subset of the lower group that we have matrix L that can be written like this, U0, P sigma, U1. So our goal is to determine the homotop type of these sets, BL sigma. In fact, let me give you a very easy example. I start with n equals 2. Like this is this is the lower group, yeah? And my first example is this one, eta, the matrix, the permutation that 1 goes to 3, 2 goes to 2, and 3 goes to 1. And the permutation matrix is this one, like this. So this is our permutation matrix. Okay, so applying the definition, the set BL eta is like this. Why we should have this? We should have this because we have a matrix that are in this set. We should have this minor determinant here. Let's say, let me explain more. The rank here should be the same here. In this case, z should be different than 0. And this minor here, xy minus z, should be also different than 0. So in this case, z should be different than xy. So, yeah?
One slide a second.
Yeah. Yeah. Here? Yeah. So what?
The Bruja cell for that is sigma.
Yeah, exactly. Exactly, exactly. So, and this first example, the permutation sigma we call like eta because they are very special, and we call like that. And this is easy for you to understand that it has 6 connected components, and all of them are contractible. You don't need any techniques to see these. But if you increase the number of, if you increase the any, or if you take another permutation, things get difficult very quick. Yeah? But in fact, if you consider eta, the Coxeter element in Sn plus 1, like that, for one any.
Just very slow. I don't understand. So in 2 slides before, you have this definition that you have this statement that if you look at you were going to be looking at intersections of top Broussard cells in another Broussard cell.
Yeah, but they will appear. For the moment, it's not clear why.
So this definition of BL sigma is such a thing, but it's not clear from that definition.
Exactly, exactly. I will need more, exactly this. So, but, and then, so what happens is that if we take this eta, this permutation, the top permutation, the number of connected components of this set BL eta is well known. And so, in fact, there is like, if we are looking for n equals 2, that we just did, the computation was 6. And if n is 1, is 2. N is 3, is 20, n 4 is 52. And from n equals to 5, the number is always 3 times 2 power n. So, but if you take any other permutation, doesn't have results until the moment about this. Okay, there is results. We can have some results, but not so clear like this. Okay, and what we did something that we introduced a stratification of the sets BL sigma that we are studying, and obtain the dual CW complex of the stratification is homotopic equivalent to the sets BL sigma. So I will explain how I get this stratification and how we get the CW complex. And so with these techniques, we are able to reproduce these results of Shapiro-Weinstein. And we also are able to say the number of connected components for all permutation sigma in Sn plus 1 for any until 4. We are able to say how much connected components we have in BL sigma for sigma in SC until SC5, okay? And we did this constructing the CW complex by hand. For example, we are going to do this here today. And so we construct the CW complex and we saw that they are contractible, okay? But if these things that looks like so simple, like they are contractible, they disappear very quick when you take any bigger. For example, when you take n equals 5, and for this permutation, 1 goes to 5, 2 goes to 6, and then we continue like this. We show that there exists a connected component, each are homotopic equivalent to a circle, and so not contractible. And moreover, we show that for any greater than 5, always there exists a connected component that have even Euler characteristic, and therefore not contractible. So let me start with some more notations for we be able to understand better what we are doing. So in fact, what I'm doing, like let's denote A1, the inversion, one change with 2, and so on, like an n plus 1 change with n plus 1, like that, the generators of Sn plus 1. In order to compute the homotop type of the sets BL sigma, first of all, we should choose a reduced word for permutation sigma. What is a reduced word? It's a word with minimal length. Let me say that the length L is the number of inversion of a permutation sigma. So, one inversion is what we are used to call inversion, pairs like that. And so my example is this one. We take this permutation, sigma. 1 goes to 4, 2 goes to 3, 3 goes to 5, 4 goes to 1, and then 5 goes to 2. And we took two different words. This first one is, let me first say that the number of inversions of this permutation is 7. We can count this here. And we took these two different words just to give an example. Let me say this A1, A3, A2, A1, A4, A3, A2. Like first here we do A1, and then we do A3, like here I can see, and then A2, and then A1, and then A4, A3, A2. Like this wire diagram means this permutation where we read from left to right, okay? Good, so. And this A3, A2, A1, A2, A4, A3, A2 is another wire diagram for this reduced word, for this permutation. So what you do, we fix a reduced word, and we do the stratification. If you take different reduced words, we have different stratification, but the answer is the same about the homotop type and so on, okay? So let me start giving more definition for we understand the stratification. So let me say the idea, what we call be an ancestry of our stratification. So we take a permutation, we fix a reduced word, okay, good. An ancestry, epsilon, is nothing else than a sequence of +1, -1, +2, -2, with length L, where L is the number of inversion. So for each ancestry, epsilon, I will explain very soon what is this. Giving examples, I will not give the definition because it's too hard for this afternoon, I think so. We want to keep things going easily. So each ancestry epsilon, we define a smooth contractible manifold that I call BLS epsilon that has codimension D, where D I call the dimension of epsilon, and this dimension is the number of times that appear -2 or +2. Well, for each ancestry, we define a BLS epsilon that is a manifold, and they are disjoint, and the union is all BL sigma. So each BLS epsilon has the dimension of L minus D. Okay, so what we get? We get the following. So BL sigma, a homotopic equivalent to a finite CW complex that we call BLC sigma, C for remind us that we are looking at CW complex, with one cell of dimension D for each ancestor of dimension D. So let me explain. Okay, let me give an example. This is a reduced word A3, A2, A1, A2, A4, A3, A2, like this. We read from left to right. And they are ancestry. Let me explain what this means. So this first example, they have this label, the ancestry. I read here -1. So we put -1 for this black disk. When you look at white disk, we put +1. And we go like this. So these are -1. And then I come here. So reading left to right. And then so -1, +1, -1, +2. +1, sorry. And then, so if I look here, this black diamond, we look at this and we put in the label -2, and this white diamond we put +2. So what it means? It means that we are in one cell in CW complex of dimension 1. And so we continue like this. This is an ancestry. And how I see two black diamonds, or in other words, 2 times -2. And this is, we are in one stratum of dimension, of codimension 2. In the CW complex, we have dimension 2. So far so good, but I want to now to explain, first of all, how are the matrix that are here in this stratum of dimension 0, in this stratum, this first stratum, the cells of dimension 0. So the matrix here, they are easy to understand thanks to the, so.
How do you decide what's a diamond and what's a circle?
Yeah, sure. Oh, how to decide how is a diamond and how is a circle? This has to do with the ideas. This has to do with, in fact, we are looking at sequence of permutation. We are looking what the permutation are doing. So, how I can explain this first one, here I look that, how I can explain, if a matrix are here, they can be written like a product of permutation in the lower group. And so the sequence of permutation we are looking is, they are all time in the identity. I never leave the identity. I will explain these in examples, but maybe I need more time. And then I'll give an example so what this means, but I will need a bit more time, I think.
So perhaps then another question. So if you give me the reduced word, so these are all different ancestries related to the same.
Exactly. If you give me a reduced word, I look for this reduced word, for this wire diagram, and I already know, just to look this, if I have ancestry of each dimension. And then, so what it means, that I already know what I'll have in the CW complex or in the stratum until the dimension I will have, things like that. Yeah, exactly. So I will give an examples because the definition, you need to define a lot of things. And so, and I will start to, yeah, sure.
So there are 4 to the power, if L is the length of the reduced word, there are 4 to the power of L.
Exactly. So, exactly.
Each one corresponds to some
Exactly. Yeah, okay.
All appear as cells in this.
Yeah. So for codimension 0 in the first.
How do you get the 4 to the power of L? So any combination of diamond or circles of black or white is allowed?
Yeah.
I thought so. Then ancestries don't have any condition.
No, they have. No, sorry. Just for this one, I have 2 power L ancestries of dimension 0. But for higher codimension positive, I have conditions that they.
Then it's not true. Is it true or is it not true that you have 4?
So maybe can you repeat, please?
So there are 4 to the L ancestries.
No, for dimension 0. For the first one, just for the first one, for codimension 0.
Yeah. Okay.
The others, no, I have conditions. So I have conditions. So the conditions, I will explain.
It's probably 2 to the power L for codimension 0. So codimension 0 means this case where you don't have diamonds.
Exactly.
That's 2 to the power L of those.
Exactly.
Okay, and they're not 4 to the power L in total.
No.
Okay, good. So there are.
You understood? But if you give me an ancestry, I can look for this. We can do this, and I know how much ancestries I have of codimension 1, codimension 2, but I can't say the number right now. Just for this I can say. Let's see, here in this case, and then so here in this case, for example, let's look here, okay, Jethro? So here I can choose the signs, change this sign, this, okay? And then for this ancestry, I can have 2 power 1, 2, 3, 4, 5. And then I can put a diamond here, black diamond here, and a white diamond here. This I know, and they didn't tell why. Okay, this is a secret, I'll speak soon. Okay, I'll try to explain this. But you understood? Did you understand the idea? Just the idea, I'm not giving...
Sure. So I thought, first you said an ancestry is a sequence of plus minus 1 plus minus 2. So there should be 4 to the power of L.
No, satisfying some conditions.
Yeah, satisfying select condition.
Some conditions that are not specified.
Ah, that you haven't said what the conditions
Yeah.
are. Okay.
Okay, so but this that you are speaking works in this case. In this case of dimension 0. Okay. Okay. And so that I will speak right now this one. So that is easy for me to speak this one. And the other I am avoiding. So in this case, let denote by lambda it, this matrix, that I have 1 in the identity and t in the entrance I plus 1 I, okay? And I fix a reduced word. First of all, fix a reduced word. And consider this product, lambda I1 T1 until lambda IL TL. So remember that all time we're fixing the reduced word. So from the works of Berenstein, Fomin, and Zelevinsky, so this vector is unique. If you write like that, this T1 and TL is unique. Moreover, for almost all L in BL sigma, there exists a vector T1 until TL. T1 until TL can't be 0, okay? That holds like that. So, if you are in an ancestry of dimension 0, so you have matrix like that, where the sign of Tj is exactly the entrance of the epsilon in the position j. So let me explain. Again, if you look for this example, here we have the matrix that are written like lambda I3, and here this entrance is negative, this entrance is positive, negative, negative, positive, negative, positive, okay? So, and like these are the answers of dimension 0. So let me come back for our, yeah?
Just a second on the next slide.
Here?
Yeah, I just want to finish reading.
Sure. I have to drink water.
Ancestry, that you defined before as well, right? It's given by some.
So this is the ancestry of dimension 0.
What's the dimension of an ancestry?
Okay. So the dimension of the answers has to do
It's there.
here, yeah, has to do. Okay. Yeah, it means that in the DCW complex, what you put is a dot. Let's see. If I'm here in the DCW complex, what you put is a dot. Okay. Very good. So let's come back for this easy example that he already saw the answer, and we are just exploring the stratification. And so we have 2 reduced words, A1, A2, A1. Let's see, go to A2, A1, A2, like a permutation, eta. And we will fix, for the stratification, this first reduced word. Okay. So, if L is a matrix in BLS epsilon, where epsilon is an ancestor of dimension 0, we know that L is written like that. Lambda 1 T1, lambda 2 T2, lambda 1 T3. In this case, what we get is these. And how much ancestors of dimension 0 we have? It's 8, just for dimension 0. And how we already spoke, these BL eta are made by matrix with that conditions. And here is one connected component. Here is the stratification of these connected components. Let's look. Here is T1. T1 is negative, T2 positive, T3 positive. And here T1 is positive, T2 negative, T3 negative. And if we look, T2 is exactly in the position of Y. These always also help us to understand. And Y here changed the sign from plus positive to negative, and it's okay. Let's say what we have in these connected components, all lower matrix, that z is bigger than the maximum between 0 and xy. And this has 3 strata. But so if you took a matrix, let's say x is 0, y is 0, and z is 1, they are in this set, BL sigma, but they are not in this ancestry of dimension 0. They are not there. So, but they are here that have a black and white diamond that just appear one time, and we call this an ancestry of dimension, dimension 1. And codimension in the stratification has codimension 1, okay? Well?
So how do we get this 3 strata only?
No, there is other stratification. I just give you an example. I will arrive there. I'm trying to do the construction, but so for explain this strata, I will need, I can do the computation of this matrix that I spoke about, 0, 0, 1, for example. I can't write this matrix like a product of lower matrix. In this case, I need to do the computation in a compact group, let's say orthogonal group or the spin group, and then I will take back the information for the lower group. Is this that we are doing?
I'm a bit lost. I'm just accumulating questions for later, I guess. But
No, you can.
so here you're saying there is one component, which is this one, the LZ. No, I already don't know why that is a component, but I can imagine it. And actually, yeah. So yeah, that looks like a component of that space. So now, these 3 stratums, I assume that they are connected with these 3 particular ancestries that you drew there.
Exactly.
And so the question is, why? I mean, there are 8 ancestries for
exactly.
Presumably,
They are 8. They will appear here. Let me, because they appear here. So I went a bit far just to show what. So they will appear here. For 2 of them, they will not appear. They are empty. And then the others are like that. So just for we give an idea. And this has dimension 0. Yeah, and this edge here, dimension 1.
oh, I see. So for each ancestry, you can actually compute a strata.
Yeah.
And
then what we see, in fact, is like if I read the condition that we get is that if I had one sign here and here I have the opposite sign, I can, let's say, click here and cross one strata of codimension positive and go here, change the sign of all.
okay, then probably my question would be
And then, for example, if you have the same sign in the each line, you can't. You can't change for, if you push that, you move for other connect components, completely different. Things are, but let's say if I want to exactly explain all of these, I need to define how I can do this computation in other group. And then I need all of these. Let me remember that this spin group is the double cover of the orthogonal group and come with a natural projection that we denote by that. And so we are looking for the spin group that are in the Clifford algebra, and I will look. We are working in the even subalgebra of Clifford. Here, this one that we denote like this. And since we are all working here all time, for ease of notation, we call this Clifford algebra. For things get more clear what you are doing, let's come back for n goes 2. Spin 3 is the 3 sphere. And the quaternion are this Clifford algebra, okay? So in our notation, we will denote by hat A1, hat A2. This hat is to remember that we are working with the generators of the Coxeter group, okay? And hat A1 is nothing else than K, and hat A2 is nothing else than I. Okay, just to remember that you're going to use this notation hat for this. And so that is these two groups, Bn plus 1 plus and Bn plus 1 plus tilde, that are very important here because they will give a stratification of the spin group and the orthogonal group. And so we denote by Bn plus 1 plus the group of signed permutation matrix with a positive determinant. And we denote by Bn plus 1 plus tilde the inverse of this set using the map pi. So, like this, instead of doing the computation with the matrix lambda, now we'll do the computation with the matrix that we call here alpha when we are doing in the orthogonal group, the computations. Here I am in the row I plus 1, and columns I plus 1. And here is the alpha when you do the computation in the spin group, and we use this hat to remember that we are in the spin group. So this acute AI, is alpha I in pi divided by 2. And this grave AI is nothing else than the inverse of the acute AI, where this acute AI are the generators of the group Bn plus 1 plus tilde. So in this case, this hat AI is, the idea is that I am generalization, the idea of the quaternion groups. So I will explain what is, I will try to explain, but it's a lot of definition, I think so. But let me say, I have the Broussard in the orthogonal group, and I want to define the Broussard now in the spin group that I call this Bruce sigma. Bruce sigma is, if I take the inverse of this cell, and I fix that Bruce Z is the connect component here that contains Z. Sorry. Because, so let's say that group PZ, if I have Z or if I have minus Z, group PZ is equal to group P minus Z. And then we fix like this the connect component of Z. Okay, like this, we can have a stratification of the spin group, like the joint union of these sets, Bruce Z, where Z is in Bn plus 1 plus tilde. Each cell Bruce Z has a dimension of the inversion of Pz. So Pz, let me put here what is P. We are denoting like that. P goes from here because it's up here, and then we arrive here. So we take a matrix, we use the projection, and then we see that the matrix just with in Bn plus 1 plus, forgetting the signs, and we see which matrix we have. Okay? Makes sense? And then we know how much inversions this has, and we know the dimension of the cells Bruce Z. Okay. So, but what we need to do is, let's say, to define, to have idea, what is these lifts of these Brujas cells in the lower group. So how we can do this? So we need a bit more definition. So the idea is that, let me take L, a lower matrix. We define bullet Q, L, exactly like Q. What you are doing? We are doing this like a KR decomposition. And we take a matrix here and we associate the orthogonal matrix. Okay. And we can lift this to the spin group, fixing that the identity go to 1. Like the identity here go to 1, and this map is well defined, and you define like 1, this set that is an open contractible neighborhood of the element 1. in the identity. Why we want to do this? For we be able to have unique L and U matrix. For this becomes well defined. It's okay. So in this case, what you do is that these maps and these maps are diffeomorphisms. So these maps is nothing else that I do the LU decomposition, and this is possible. They are well defined because the condition that they are open neighborhood, contractible neighborhood of the element 1. And we identify a matrix here with these elements, ZL tilde, in the set U1. And if I take L in BL sigma, we can define a matrix, finally, we can define a matrix here in Bruce sigma. So here now I think it's more clear that appear the intersections of Bruch-Hassel's. So how we get this? So this BLZ is diffeomorphic to these intersections of these two Bruch-Hassel's, so that are a subset of the lower group. So for this, we did all of this construction for this, for C that BLZ is diffeomorphic to this. So in fact, this is an open, this is a big cell, the top dimension cell, and this is an arbitrary cell. So now, okay.
Sorry, I didn't understand the definition of Q. Could you go back?
Okay. Yeah? Yeah, you can do this in orthogonal group and then lift. But I put just like this for get short, okay? Okay, so very good. So more than this, like with these, with all these, we get that BL sigma can be right like this disjoint union of BLZ, where Z is here in acute sigma quat n plus 1, where what is quat n plus 1 is the idea of the generalization of the quaternion groups. So this is a normal subgroup of order 2 power n plus 1. Okay? So in this case, things get, let's say, more, I have more idea what I'm going to do. So, okay, in this case, what you are going to do is take in here from this, take a sigma here, look how elements here goes down, and do the stratification, do the CW complex for each one of these. So let me come back for this, my first example. So my first example was this, if you remember, n equals 2, and we are taking A1, A2, A1. The permutation eta, we are writing like A1, A2, A1. Well, by minus 1 of eta, there is 8 elements like this. My minus, we have 4 here and 4 here. And here I denote like that, like if I put some signs here, what I should do with the elements. So if I put plus, 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 it means acute, acute, acute. So acute A1 is 1 plus A1 hat divided by square root of 2. And A2 is 1 plus A2 hat divided by square root of 2. And we do this computation, we arrive here. And then we do the computation for plus, minus, plus. In this case, is acute 1, grave A2, acute A1. And we arrive here. And we go like this, okay? And what we get is this. And then we saw that we have 6 elements, 1, 2, 3, 4, 5, 6. 2 of them doesn't appear here. They are empty. I think is minus 1 plus A1 hat, A2 hat divided by square root of 2. And I think it's minus 1 here, minus 1 minus a1 hat, a2 hat divided by square root of 2. Okay, so this is our stratification. And if I look here, is minus 1, plus 1, plus 1. And we are exactly here. And we have 2 ancestry of dimension 0. And we have an ancestry of dimension 1. So, what happened? Let me explain more. Like we know one formula for each z in Bn plus 1 plus tilde. We know how much ancestry of dimension z we have. So why this is important? So we can double check our computation. For example, we can look a reduced word. We can start put signs and clicking in its cells and changing clicking the cells that we can click for the situation, let's say. But we can double check if you're not missing any cells and things like that. So the formula is easy. Let's say B, I take most of the time they are 0. They are not 0. Just when, for example, we can write a permutation like we can divide the permutation like in blocks. They don't mix here with that. So this doesn't happen in general. And then, so the number of cells of ancestors of dimension 0 are given like that, 2 power L minus N minus 1 and plus this, where we denote by this the real part of this element. So I'm just giving an idea what it means. And this is easy to computation. So for example, for eta 3, 2, 1, like this, L is equal to 3, N is equal to 2, B is 0, and Z is given like that. So if the real part of Z is 0, we have just one ancestry. If the real part is minus 1 divided by square root of 2, no, in this case we have 0. And if the real part is 1 divided by square root of 2, we have 2, like we saw before, okay? Well, so there is more information that help us to understand or to double check, to put easier our computation. For example, there is a action of in the signs, in the group of signs, that if you take 2 elements in Bn plus 1 plus tilde that are in the same orbit, you just need to do the computation for one of them. So the other will have the same answer. So moreover, if you have like Z0 equals minus Z0, in this case, this orbit has the cardinality of 2 power N minus C plus 2. If it is happen, for example, what we have is that the real part is different than 0. No, it's equals 0, sorry. Here is different than 0. And in this case, these orbits, they are disjoint, and each of them has this cardinality, okay? So, some more applications for we try to understand what's going on. Yeah. So this example, N is 3. This is the set law for 1. And if you take this permutation, sigma, for 2, 3, 1, we can take, for example, this reduced word, A1, A2, A3, A2, A1, and this is our permutation matrix. And applying the definition for we being this same Bruchsal, what you should have is that this guy should be different than 0, and this determinant here should be 0, and then this should be 0, and so on. We have this. And so how we can do the number of, we can say the number of connected components of this example. So let's start with all this stuff we already spoke about. We should first compute this. and we have these 16 elements. And so for the action of this group of sign, we have 5 orbits, and we know the size of the orbits. So they have size 4 or 2, and for each z here that we know, we can see that the real part is plus 1 divided by this, or minus 1 divided by this, or 0, yeah? And so how much ancestries we have? If the real part are this, is 0. If the real part is 0, we have 2. And if the real part is 1 divided by square root of 2, we have 4 ancestors of dimension 0, okay? What happened? So let's see. After some computation, here BLE acute sigma has size 4. Here are the connect components that are disjoint. Like we can pay attention that in the same line for the same generator, we have the same signs. Let's see. And so this is the 2 connect components here times 4. From this we already have 8. And then this is size 4. We have here 1 representative for this set. And so this we can see that this is contractible for here and then for here. And this is a square, a cell of dimension 2 that glues like that. So, and here we have 2, size 2. In this case, we have 2 plus 4 plus 4 plus 8, I think so. I counted correct, so yeah. And then we have 18 connect components. Okay? Good? Okay. So, what you maybe probably are asking is, it's type of matrix you have here. That was a question that you did me in the beginning. What type of matrix you have here in one stratum of codimension 2, for example? So, because if you are in a strata of codimension 0, it's easy for we see. So I took an example. We constructed this using Maple. So in fact, we use a lot of Maple to do our computation or to double check our computations. And for example, I took this matrix here in this BL sigma that so satisfies the condition to stay in the set. And we took the orthogonal part of this matrix. Let's say we did the KR decomposition. The orthogonal part is this one. So here we did the computation in the orthogonal group, not in the spin group. The orthogonal group was easier. We wrote this matrix like a product like that. So we are using the alpha 1, alpha 2, and so on. And so let me try to at least give an idea what we are doing. Let's say this is A1, A2, A3, A2, A1. Yeah. So I'll try to do like this for we construct our stratification, and then we do A2, and then A3, and then A2 again, and then A1. So, from our conditions, so we know that if we look for this, we can put a black diamond here, or here, like this, and white diamond here, and this I can put black or white disk, but I can see that we only have these answers of dimension 2. In this case, we just have 2. Here can be white or black. Okay. So for this example, we wrote like this product, and what we saw is that always we should start and end in the same sequence of permutation matrix. We should have time to start and to start and end in the permutation eta. So you start and end the beginning. In this case, let me start. If I start rho 0 is eta, I pass here, I took one generator. Each generator I took A1. And then I put the A1. And the number of inversions, rho 1, I think is 5. So if someone can, okay, we can do the computation, but the number of inversion went down. And then, so I should took this generator and I put -2 in this label, -2. And then I do this again, I look here, I am passed for this generator, I choose. So, and I took there, rho 3 is eta, A1, A2, I put there the generator, the number of inversions went down again. And then rho 4 is like that. So look, I need come back, I need to have time before I come back to the permutation eta. In this case, I can't take the generator. And I should, and then back take this one, A2 and A1. And I start and I come back in this, so these conditions. And what happens is that if I decide to put there, in this one, that we didn't know if were, let me say, black or white disk here, we look there, the sign where we wrote this product, and there is a minus. In this case, we put there -2, -2, -1, +2, +2. This is an example of one matrix in this stratum. Okay. So this is the idea of the theorem. The theorem A.2. In this theorem, what we are saying that there exists a connected component of BL sigma, it's a homotopic equivalent to a circle. What we did, so in fact, what we did is like we took an example, a matrix sigma, and we wrote like this product, and in this case L is 12, and we compute exactly the number of cells of its dimension. Let me say dimension 0, what we have is 48 cells. Of dimension 1, we have this number, 2, and we don't have strata or cell of dimension higher than 2. And in this case, we did the Euler characteristic and we get 0. And we construct by hand this stratification, this one. And so if we start, for example, with this distribution of signs, we can see that I can click here and I move from this cell to this one, change the signs in the boundary here, okay? If I click from, let me see, I can click now here, and we are going to move from where? So from here. And then we're going like this, so pay attention that we have an edge here, because we are clicking where? I think so. We are clicking here, and we construct like this. And then this double complex is this one, so I think it's easier maybe for we see. And we have this double complex that we know that's not contractible. So what happens is that the things get complicated very quick. For example, when n is 4 and the permutation is eta, already Shapiro and Weinstein compute the number of connected components for this set, and they have 52. So we did this also with our construction, but we already saw that we have a cells of dimension 4, and we are not able to do construct using these ideas. We prove that they are contractible using other things, and this is the problem. Let's say the construction they get complicated very quick. So for example, for n equals to 5, we And for the permutation, we know that always exists a connected component here with Euler characteristic. So I'm doing here one example. We see that things already become complicated. We took here the real part negative on purpose for the number of answers becomes not so high. And for example, we know that these have Euler characteristics equals to 2. They are not constructible, but we didn't know how to compute the homotop type yet. Yeah, for this example. So this is what I wanted to speak today. So if you want to see some definitions, I can write and I can speak more. We have time. So thank you so much for the attention. We can speak about the details. Okay?